Hello everyone. In this session, we are going to have a step forward from pipelining. We will see how a normal computer system is incapable of doing a certain kind of a task in which we do require a more advanced processors or computer systems. Of course, when you do have a laptop or a desktop, you know that it is capable of doing many kinds of a task, including your program execution or watching a 4K video or executing any complex task which is confined to be a personal use. But when it comes to a huge computational task, very complex task, such as receiving the pictures from a space station or identifying the resolution that has been sent from a space station from another planet. Of course, there are a few computational tasks that cannot be performed by a regular computer system. Although any regular computer system is capable of doing anything, but these computational tasks may require days to be executed. For that reason, we do require an advanced computer systems, such as mainframes, to process these kinds of a task. As you can see on the screen, there is a class of computational problems that are beyond the capabilities of the conventional computer systems. I can't say the conventional computer system cannot perform this task. A conventional computer system also, since it is a computer system, it will be able to perform any kinds of a task. But the time that is going to be taken by these computer systems are huge. So definitely we do require a better computer systems when it comes to executing a complex task. These problems require a vast number of the computations that will take a conventional computer days or even weeks to complete. These computer systems, let us say the advanced computer systems, will be called as vectored computer systems, vector processors. Some applications of this vector processor are long range weather forecasting. You know that every day you're going to watch this weather forecast. This weather forecast that is identifying the pictures that are sent by the radar and analyzing them cannot be done by the regular system. That can only be done by a vector processor. Of course, seismic data analysis and the aerodynamic and space flight simulations and the petroleum explorations and the medical diagnosis, all these kinds of areas do require a huge computational task in which we do require a vector processors to be used. When it comes to a vector processor, of course, the definition goes like this: ability to process vectors and the matrices much faster than a conventional computer. Let us understand the difference between a conventional computer system and a vector computer system. Let me talk about the way of performing the operations in between these two kinds of different systems. Let us understand that I would like to perform a task. That is, I would like to add two vectors. That is, rather two arrays, let us say. I want to add two arrays, A of 100 and B of 100. There are two arrays, one is A of 100 and one more is B of 100. If I would like to add these two arrays, a typical normal program will look like this. Of course, here the Fortran language is used. First of all, we need to initialize the count variable I is equal to 0, after which we need to read each of the element from A, and we need to read each of the element from B, and we need to identify a storage location, that is the destination location, in which we named it after C. So the C array is the destination array to which the products are, the addition values will get saved. So C of I is equal to A of I plus B of I is going to summarize the operation that is going to be performed here. And we need to perform this as many times as required in order to perform the complete task to be done. So if I is not equal to 100, we go to the label 20, and this will be in an iteration. It goes till the entire computational task is going to get performed. But you know that there are a lot of instructions to be executed in this case. In order to simply execute two arrays, if we have to execute too many instructions, what about a complex application? This is what we are talking about. A conventional computer system doesn't have any time restriction. If you want to execute a program, there is no practical restriction on the time that is to be executed. But when it comes to a complex application to be executed, there has to be a restriction on a time. We expect that task to be finished within a stipulated time. Executing a complex program for a simple operation for adding two arrays, one is A and one is B, is not going to prove a computer system a better one. For that reason, we're going to use a vector computer system. In a vector computer, simply in one instruction, everything can be easily done. Although the operations will be in multiple, the instructions that are going to be executed will only be one. Here, simply C of 1 to 100 is equal to A of 1 to 100 plus B of 1 to 100. The instruction that is going to be executed is only one. I don't need to execute hundreds of instructions in order to perform the operations. Right after the instruction is executed, all the operations will take place in the ALU directly. This is the beauty of the vector computer. Since this is a complex processor, we don't require much time to perform the same operation. Here, let us understand how a matrix multiplication is going to be performed. Let us have a look at the vector instruction format. The vector instruction format will look like this. You know that the normal instruction format will have an opcode followed by operands 1, operand 1, operand 2, and operand 3. This is the normal instruction format in a conventional computer system. But in a vector processor, the instruction format will look like this. We do have an opcode, and we do have an address at the source 1. We do have an address with the source 2, and we do have an address with the destination. Of course, still this, it is pretty much similar to the normal instruction which we can experience in the normal computer system. But in addition to this, we do have one additional field in a vector processor that is called a vector length. This vector length will give you the number of operations that is going to be performed. In the result of this instruction execution, as a result of this instructions execution, how many operations are needed to be performed in the ALU will be depicted in the final field, which is called the vector length. These are the vector field, here it is 100. So the number of operations which are going to be performed by this opcode are equal to 100. So I don't need to execute 100 different instructions. Once after the instruction is fed, it's just all about the ALU to perform the different operations. That's it. We don't need to execute different kinds of an instruction. Rather, we don't need to execute an iteration of instructions, repeated instructions. Instruction could only be one, but the operations that are going to be performed will be equal to the length of the vector. Let us consider a matrix multiplication. Here, there is a matrix A, there is a matrix B, and the product will be another matrix which is C. So, a 3 by 3 matrix and another 3 by 3 matrix will be multiplied and is going to produce another 3 by 3 matrix that is equal to C. Of course, by using a conventional computer system, it takes a lot of time because there has to be too many instructions executed. So here, if you want to get one element in C, you know that A11 plus B1, A11 into B11 plus A12 into B21 plus A13 into B31 needed to be performed. Now let us have a look at how a vector processor is going to perform this, because why we are taking, let us understand why we are taking matrix multiplication. In all these applications that we have stated, the elements will be stored in the huge arrays of matrices. So when it comes to processing an application, we may deal with a huge number of matrices in which the matrix needed to be added or multiplied or divided, any kinds of an operation that are going to be performed only on the matrix, because all the elements will be stored in a huge class of matrices. This is the reason why. Let us take an example of matrix multiplication and how a vector processor will be able to perform its operation on this matrix multiplication. Now, let us understand, we do require a pipeline. There is a pipeline for addition and there is a pipeline for multiplication, because the operation that are going to be performed in this case is, one is multiplication and another one is addition. Here we assume that the multiplication, there are 4 segments of multiplication and there are 4 segments of addition. The addition ALU unit has 4 segments. Similarly, the multiplication ALU unit will also have 4 segments. Let us understand this. This is the multiplier pipeline. This is the addition pipeline. You know that addition and multiplication cannot be done at a single stretch. In the ALU, there is a segment called addition, will only perform addition. Similarly, in the very ALU, there is a segment called multiplication, can only perform multiplication. So first, the operation that is going to be performed is multiplication. So what we do is, we will initially multiply the product and then we feed it to the adder pipeline. Then finally the product will be added. Let us see what is going to happen here. So multiplier pipeline, as you can see, has 4 segments. Addition pipeline, as also you can see, has 4 segments. Initially, during the first clock cycle, A1 will be fetched from the source A, B1 will be fetched from the source B. After which, in the second clock cycle, A2, B2 will be fetched. Third clock cycle, A3, B3 will be fetched. Fourth clock cycle, A4 and B4 will be fetched. Right? So in the fifth clock cycle, A1, B1 will get transferred to adder pipeline. So in the cumulative process, at the ninth clock cycle, you will get A1, B1 out of the adder pipeline. So this A1, B1 in the ninth clock cycle will be input back to this adder pipeline. Since adder pipeline cannot function unless there are 2 products, A1, B1 has been multiplied, and in the fifth clock cycle, A1 and B1 are fed to the adder pipeline. Since the adder pipeline has nothing to do, we'll just pass this A1, B1 to the next segments in the subsequent clock cycles. In the ninth clock cycle, A1, B1 will be fed back to the first stage of the adder pipeline. So in the ninth clock cycle, you also can understand A5, B5, you're going to get it from the multiplication pipeline. So in the ninth clock cycle, the first product, that is A1, B1 plus A5, B5 will be added in the first adder pipeline. This is how a vector processor is going to perform a matrix multiplication. Now you can clearly see this is right after the first 8 clock pulses. In the first clock cycle, in the first clock pulse, A1, B1 will be here. In the 8th clock pulse, A1, B1 will be here, and A8, B8 will be here. Till now, the production, that is multiplication, has been performed, but the addition hasn't been performed. In order to perform the addition, we do require 2 products. So at the 9th clock pulse, the first addition will get started. At the 9th clock pulse, what happened? A1, B1 will be sent out of this pipeline and will be fed back to the adder pipeline. So A1, B1 in the 9th clock pulse, where is the 9th clock pulse? Yes, in the 9th clock pulse, A1, B1 will be sent back to the adder pipeline. At the very 9th clock pulse, we are going to receive A5, B5 from multiplication pipeline to the adder pipeline. In the first segment of the adder pipeline, A1, B1 plus A5, B5 will get performed. So similarly, 10th, in the 10th clock pulse, A6, B6 plus A2, B2 will get performed. In the 11th clock cycle, A3, B3 plus A7, B7 will get performed. So as the clock pulses are getting accumulated, the addition, the final product, is going to be achieved by this pipeline. Now you will be able to clearly understand how this vector processing computer system is more capable than a normal computer system. In a normal computer system, the pipeline is also pretty normal. Here, in the normal computer system, let us understand, a pipeline system is always static. When there are 4 segments, all the 4 segments are considered to be linear. So there will be an input and there will be an output. Once after the input is given, there will be an output expected. Right from the output is taken, we don't get this output sent back to any of the stages. But here, in the vector processors, we use dynamic pipelines. In the dynamic pipelines, even after we collect the output can be used once again in one of the stages to compare the products again. This is the difference between static pipeline and a dynamic pipeline. In the vector process, we used to use the dynamic pipelines. In the dynamic pipelines, of course, there is a fetch unit. After several units, there will be an output unit. But unlike the static pipelines, all these segments can give or take the information from any segment. In the static pipeline, let us say there are 2 segments. These 2 segments are positioned one after another. So this will be a receiving segment and this will be the source segment. Source segment will supply the data to the received segment and receiving segment will receive the data from the source segment. And these are unique in the static pipeline. But in a dynamic pipeline, any segment can get data from any segment. Here you're witnessing one of the dynamic pipelining techniques that are used in the vector processors. Of course, when it comes to the vector process, we don't execute too many instructions. By executing only one instruction, we'll be able to perform a huge class of computations within the ALU. So fetching the instructions and storing the instruction code within the processor, as you know that it takes a lot of time, will be reduced. Thank you.